Welcome. Today we will be taking a look at the notes worksheet entitled Sequences Day 2. And this definitely just represents an extension of yesterday's lesson, where if you remember, what we did was just explored and introduced the concept of a numerical pattern and an algebraic formula in order to represent it. And we did that primarily through the use of what is called an explicit formula. That would be in terms of our input, or in terms of n. So n was our independent variable there. And so today what we're going to do is explore an alternative way to represent a sequence, a pattern of numbers. And so we'll go ahead and start it out with an investigation at the top here with the Fibonacci numbers. And if you remember yesterday, I just did a little tie-in with the Fibonacci numbers and Pascal's triangle. These numbers were kind of hidden inside Pascal's triangle, which is kind of fascinating. And what we found is it's really not feasible to write an explicit formula for the Fibonacci numbers. But what we're going to do, as I said, is try to look at it from a different vantage point and still represent it algebraically. So let's give it a try. I'll just read what I have on your paper to be formal here, and then we'll move forward. So it says, instead of writing an explicit formula in terms of n for this sequence, we are going to write a formula in terms of its outputs. So instead of the inputs, we're going to actually write it in terms of the outputs. I don't think we've seen something like that before. So it says, let's pick a term from the sequence and label it a sub n. How can we represent the previous term, the second previous term, the next term, etc., etc.? So, you know, I don't think I'm actually going to put the numbers in here, but I guess here's what we're going to sort of think about. Inputs and outputs going together. So I guess if I have an input of n, and I'm hoping everyone's all right with me just putting it above like that, then the output would be the value of the nth term, a sub n. And so I guess what I'm thinking of is, what we need to kind of do is think about how would we notate the value of the previous term? Well, in terms of the input, everybody, if this is n, the previous input, I'm hoping everybody would be in agreement, is n minus 1. So if this is input 6, then that's input 5. If this is input 100, this is input 99. So whatever the case may be, if this is our current input, the nth term, then this is what is called the n minus 1th term. And as a result, the notation that would be used would be a sub n minus 1, the value of the n minus 1th term. Okay, now Fibonacci is actually all based on, as we saw yesterday, adding the two previous terms. So it's going to be a little unique compared to some of the other patterns that we're going to see today. But Fibonacci requires us to have the two previous terms added together. So I think it's going to benefit us to represent that second previous term as well for our purposes here. And so if I go back in my little continuum here, this is n minus 1. I'm hoping one further back, you see that this is n minus 2. So again, just in terms of if this is term 100, this is term 99, this is term 98, etc., etc. And so as a result, this would be the input, and as a result, that would be the output. And so now we can start to put a few things together here, and I think I'll leave it at this stage for now and move on to the next piece. Do I have a way to potentially write a formula for a sub n? Well, the way the verbal description goes is I'm supposed to add the two previous terms together, the value of this term and the value of that term added together. Give me the value of this term right here, whatever it may be. And so I think we have a chance at this. Let's see. So on your paper, everyone, if you could write a sub n equals, and by definition, just trying to translate the verbal description up above, is to get the value of any term, I add the value of the two previous terms. So that notation would go for the first previous term, and this notation would go for the value of the second previous term. And that looks great. And in essence, the value of any term is the value of the previous term plus the value of the second previous term. Now, that's probably about 95% of the way there, and it's looking good. But here's the sole dilemma that I see with this one. If I gave you this formula, and you totally understood the description here, you knew exactly what to do, but you knew nothing of Fibonacci's numbers up here, you would look at this and you would say, okay, I'm supposed to add the two previous terms, but if I asked you to start out this sequence, would you know what to start with? Would you know inherently that this starts at 1? No. So the one thing that's missing here is a foundational piece, the starting point, the reference point. And here, I need to define specifically that we're starting, the first value is 1. Now for the most of these formulas that we're going to write, this will be satisfactory. As I said, the Fibonacci numbers are slightly unique in that we need another one too, right? So this gets me going. I know the first term is 1, but this description right here, we need 2 previous terms. So as a result, everybody, here's what you're going to do. Oops, let's do a sub 2 there. A sub 2 is also 1. Now, if I gave this to you, you would know what to do, and you would be able to come up with the values for this particular sequence of numbers. And don't write this on your paper. This is just how you would look at it. This wouldn't get you started because you don't know the value of the previous term or the value of the second previous term. So I come over here and I say, all right, the value of the first term is 1. Now this says to get any term, I add the 2 previous ones. I'm not there yet, so I need another foundation. And so I know the second term is 1. Now I've run out of given terms, so I have to come up over to my algebraic rule, and it says, okay, to come up with any term, I add the value of the previous term and the value of the second previous term. So to come up with a sub 3, I add a sub 2, which is this, and I add a sub 1, which is this. And if I add those together, 1 plus 2 is, oops, sorry about that. Add them together, and of course, I get 2. And then I go back. If I want the fourth term, well, I add the third term and the second term. Third term, second term, and then dot, dot, dot. It's what's called a recursive loop. So now it just reverts back, and I can get the next one. Reverts back, get the next one, and then it goes on, obviously, indefinitely. Okay, good. So that's exactly the type of formula we're going to see today, and it is what is called a recursive formula. So let's go to your notes worksheet here. Here's where it says recursive formula. Couple things started out here. Generally speaking, this will be the case. The first term has to be stated. Once you have that first term stated, you know where to start, and then you have the algebraic rule to tell you to go where to go from there. So, and then a rule for, and this is generally how they're going to work out for us, obtaining any term based on the preceding term, the one that goes before it. All right, so we need to state our first term, and then from there have an algebraic rule telling us what to do. Okay, so just a couple here. These are rather good ones, by the way, and we'll go ahead and take a look at those and then sort of move forward here with a couple other pieces. So example 1 on your paper, everybody, it just says list the first 6 terms. So first and foremost, let's just kind of get our little pattern taken care of, and then I'll do some work around this. But it looks like by definition, I have a starting point of 5. So 5 is the value of my first term. Now what I need is the value of the second term, and the value of the second term will be based on the value of the first term. So I'm going to just jot a few things down because it's going to take a little while to get used to. But a sub 2, so this is the value of the second term, is defined as taking 2 plus 3 times, this officially would be a sub, n is 2, so 2 minus 1, which is 1. And everybody, of course, this was given. The value of the first term is 5. So you see that it would be 2 plus 3 times 5. And 2 plus 3 times 5 would give you 17. So there, everyone, would be the second term. Again, I'll just keep doing some work off to the side. If you know how this is going to work, great. Go with it and then try letter B. But for right now, I'm going to go ahead and take a look at the value of the third term. So the value of the third term would be taking 2 plus 3, and then if n is 3, then that goes in here, and this would be 3 minus 1, which is 2. And as I said, here's your recursion, everybody. This we just found. It uses the value of the previous term. So this is now just 2 plus 3 times 17. And 2 plus 3 times 17 should be 53 from what I'm seeing. Okay, very nice. I'll do probably one more here and then get a couple others taken care of. But let's see, a sub 4 now, just sort of finding a spot for me, is 2 plus 3 times the value of the previous term. So I just use that value and plug it in, and I end up getting 161. All right, to get the fifth term, I do 2 plus 3 times the value of the fourth term. So that would be this piece right here. And you can see they're getting fast in a hurry, about 485 on that. And then the last one, just going to try to find a little room right in there. About 2 plus 3 times the value of the previous term, so 485. And if I do this calculation here, really not too bad, but if I do that calculation, I get 1457. And there, of course, would be your first 6 terms. One given, and then each one used the previous term to find it. We used the 5 to get the 17. We used the 17 to get the 53, etc., etc. All right. Good. Let's move on to letter B. Here's another one. What's kind of interesting about this, of course, is it does use the input, but the fact that it uses the previous output here means it is recursive. So it has kind of that combination feel, right? It input and output together, but this would still fall under the line of recursive. So anyway, let's see what we get. Here's my 1. And so a sub 2 would be taking now the input. Here's my input, everybody. I'm in the second term, so the input is 2. And 2 times the value of the previous one, so 2 times 1. And 2 times 1 is 2. Good. All right, a sub 3, everybody. Let's see if we can do this one. A sub 3. 3 is my input, so 3 is my n, times the previous output, so the previous term was 2. And 3 times 2 is 6. Oops, didn't mean to have a multiplication symbol in there. So 1, 2, 6. How about the fourth term, everybody? So I'm going to have my my 4 right here. So this is my input, 4, and then times previous output, which is 6. 4 times 6 is 24. Excellent. Next one, everybody, a sub 5. So input times the previous output. That's the best way for me verbally to describe it. We're on the fifth term, so the input is 5. Previous output is 24. 5 times 24 is going to give us 120. One more. Here we go. And let's see, a sub 6. So the sixth term times the previous value. 6 times 120, and should be 720. And you can see each value is dependent on the previous one. This is dependent on this. This is dependent on that, etc., etc., back to the very first one which was defined. Absolutely awesome. Now, here's the thing. Before we move on, I am just curious if these numbers look familiar. We saw them briefly, so I wouldn't expect it necessarily for the light to go on. But basically, 1, 2, 6, 24, 120, 720, they are, by definition, do you happen to know? Hey, they're your factorials. Everyone take a look. 1 factorial, 2 factorial, 3 factorial, 4 factorial, 4 times 3 times 2 times 1, 5 factorial, 6 factorial, etc., etc. So here is a great program, so to speak, a formula to go ahead and evaluate our factorials. So pretty neat. This formula right here gave us our factorials. All right, good. So again, if I give you the the formula itself, you're able to sort of tell me the pattern of numbers. Now here's an interesting question. Which type of formula is more convenient if you want the 100th term in the sequence? So explicit or recursive? What do you think there? If I wanted to just jump to the 100th term, so the value of the 100th term, a sub 100, which would be better? And I guess the argument probably could be made that it's going to be this. Because if I have the input, if I have n, and that's what this would be, if I have the 100th term, or I should say if I have the input of 100, I can plug that in for n and easily figure out the value of that term. Whereas recursive, as you can see, the 100th term is dependent on the 99th, which is dependent on the 98th, et cetera, all the way back. So if I had to get the 100th term right here, I would have to keep going and going and going all the way up. So you can see just sort of interesting to think about, but explicit is definitely the more convenient if you want just any term right away. Okay. Well, let's do example 2. It says write an explicit and recursive formula. Okay. Well, let's go for both. So how about on your paper, everyone give me an a sub n equals, and how about an a sub n equals? And let's see what we want to do here. Now, I would argue most students probably, and most people for that matter, probably think recursively. You sort of know what the next term is based on this, based on this, based on this. You're seeing what's going on from one term to the other. And so you would know what I'm doing to the previous term in order to get my next one. So what do you say we go ahead and write the recursive one first? Let's start with that idea. Then we'll see if we can translate it into the explicit formula, which I think doesn't come quite as naturally, but we'll see. So I'm going to do my recursive one just down here. And I'm hoping everyone's okay with the fact that I would add 3, add 3, add 3, add 3. So to get the value of any term, I just very simply take the value of the previous term and add 3. And that's it. So to get my next term right here, I would add 3 to the previous term. 16 plus 3 is 19. To get the next one, I'd add 3 to the previous. And that's great. There is obviously only one dilemma. If I gave you this cold right here, you wouldn't know where to begin. So we need to at least have a way to start. Now I know the first value is 4. And to get any one after that, I just add 3 to the previous one. So that's recursion. Now explicit is going to be a little harder, but this is going to lead into some things we're going to do over the next couple days. Again, it looks like we are repeatedly adding 3. And as I said, I think we've seen this once or twice before. Repeated addition, everybody, is multiplication. So if I am repeatedly adding 3, I have a feeling we're going to have a 3n sort of sitting in our formula one way or the other. Now, unfortunately, and I'll just have to do my inputs right underneath, 1, 2, 3, 4, 5. But basically, 3 times 1 is not 4, 3 times 2 is not 7, 3 times 3 is not 10. But I'm hoping you would see that all you have to do is add 1. And that should work. So if I wanted the 100th term, there you go. 3 times 100 plus 1, got it. Here, the 100th term, well, unfortunately, I'd need the 99th, and I'd need the 98th, et cetera, et cetera. Cool. Let's see if I have some room on the board here. I'm going to try to tuck this in. Let's do it one more time. Okay, how about this one? So let's do recursive first. What am I doing to go from here to here to here? Sorry about that. So what would I do to go from one to the next, etc.? It looks like I'm repeatedly multiplying by 2. So to get my next term here, I would take the previous number and multiply it by 2. So you can do it either way here, but it looks like 2 times a sub n minus 1. And again, the only dilemma, just please don't forget with recursive formulas, I need a starting value. So a sub 1 equals 3. Okay, nice. Now, here's the situation. This one's going to be a little harder for us, but we will pick this up in just a couple days, and we'll be able to write a formula for this with great ease. For right now, it might not be so easy. So I might just kind of guide you along and have you not worry about it too much here. But I'm hoping you do see that, yeah, we are repeatedly multiplying by 2. And repeated multiplication, as we all know, is an exponent, right? And so to me, I know that we're going to get a power base 2 in there somewhere. So this is going to be 2 raised to the something or other. Now, again, just to kind of get this moving along, you do need the 3 out in front. And it's not 3 raised to 2 to the n. It's pretty close. So if I do, this is my first term, this is my second term, this is my third, fourth, and fifth. Well, as a matter of fact, this is 3 times 2. This is 3 times 2 times 2. This is 3 times 2 times 2 times 2, etc., etc. there. So this is close. But what we will see is you need a little n minus 1 on that. Try it. Again, I won't hold you accountable for that just yet. But in the near future, we'll see this in action as one of our 2 primary types of patterns, and we'll be able to work it out. But it would be 3 times 2 raised to the n minus 1. Check it out if you get an opportunity. See if it works. If you put 1 in there, do you get 3? 2, 6, 3, does it give you 12? And it should. Okay, good. So explicit formulas and recursive formulas. Now, everyone, we're going to sort of switch gears a little bit. One of the other things that we're going to be doing in this particular unit is looking at the sum of the pattern of numbers. So we're going to have a particular pattern, and what we're going to do is just very simply add them all together and get a sum. And this notation that we're going to see is a very compact way to represent the sum of any particular amount of numbers in a sequence. So it is what's called either sigma notation, sometimes called summation notation. So you'll hear me probably use both terms there. Sigma for the Greek letter sigma that's used. And so just try to take a look at this. We'll see if we can translate what's on your paper here. But basically, I would have the value of all these terms in a sequence. And very simply, I would want to add them together. So this is the sum of those values in a sequence. And instead of writing it out in a very expanded form like you see up here, all of that can be written in a very compact way, as you see right here. This is all of this. So let's talk about a few things here. Anytime you see that sigma, that indicates that we're going to be using a sum. So sigma means you're going to take all the values in the pattern and add them together. Okay, now number 2, it looks like a couple things we're going to have to deal with. This a sub k right over here, k being our variable, this is just going to represent the value of the kth term, essentially. So that's what I'm going to write here. A sub k represents the value of the kth term. So k just sort of substitutes n as our variable, as our independent variable. So rather than using n, because n is actually used elsewhere in this notation, we're going to use a k as a different variable there. But it basically means the same thing. K would be your input, a sub k would be your output, the value of that particular term. Now k, as sort of alluded to, is very simply what's called the summation variable. So again, it's just the variable used. There we go. So k is the summation variable. Now you see one other piece to the puzzle here, down below and up above everybody. Very simply, this down below tells us what is the input that we're starting with. So when you see k equals 1, that means we're starting with the first term, then going to the second term, then the third, then the fourth, all the way up until this top number right here. So we would be going from 1 all the way to n. And here it is. If you look right here, here's your input of 1, 2, 3, 4, 5, all the way up to the value of the nth term. So from 1 to n in terms of your inputs. This tells you where to start, and this tells you where to stop. So I'll go ahead and write that piece up here. And obviously, a lot of this is it's going to be difficult until we actually see it in action. So 1 and n represent the smallest and largest inputs, essentially. And now we know our inputs are the k values. Okay. Again, we'll try to put it all together here, and we'll just kind of go both ways. We'll do the easy way first, though, of course, whereas if I go ahead and sort of give you the sum represented in the sigma notation, can you go ahead and evaluate it? So in this case, we'll expand it all out and then get an answer here. So let's give it a try. Everyone just put a little equals off to the side. I'm going to do just some work over here because I have the room over here. But basically, what we're going to do is put in inputs for k. K is our variable, and we're going to substitute numerical values in there. And our inputs would start at 1, then 2, then 3, then 4, then 5, then 6. And because 6 is our top number, that's where we stop. So essentially what we're going to need, everybody, is the value of the first term. So I need a sub 1, a sub 2, etc., etc. Just like we've been doing before. The only difference here is instead of writing out our numbers and putting a little comma in between each, is we're going to eventually add them together. This is what is called a series, which we're going to see over the next few days. So let's go for it. A sub 1 means very simply put in 1 for k. 1 squared plus 1 is 2. A sub 2, so then I do the next one. 2 squared plus 1. 2 squared plus 1 is 5. Next input is 3. 3 squared plus 1 is 10. Okay. Next input would be 4. 4 squared plus 1, 17. Next, 5 squared plus 1, 26. 6 squared plus 1, 37. And now I stop. This told me the smallest input. This told me the largest. And I go in sequence. 1, 2, 3, 4, 5, 6 is the inputs. These are our outputs. And so now, again, instead of writing them with a comma in between as sort of the first 6 terms, very simply, I want to go ahead and add them all together. That's what the sigma represents. It means actually get a numerical sum. Oops, missed one. So add the 37. And guys, if you get an opportunity, grab that calculator for a moment. And let's see, I don't have it, so I guess I'll go ahead and just bring it up for kicks. And here's what I have. So I'll do 2 plus 5 plus the 10 plus 17, 26, and 37, everybody. Add those together, and I get 97. And so that is our overall answer. Perfect. All right. Hey, let's try this one. So now, again, sigma means we're going to add our terms. I'm going to start with the first term and go to the 5th term. And k being our variable means now we're going to substitute those numbers in and find out what we get with this algebraic expression right here. So it looks like it's just a factorial. So 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial, 24. And 5 factorial is 120. And so let's see if I can pull this off here. Just add those together. And I'm getting 153 on that. Hopefully that's the case. I'll box it up and we'll move forward. So I'm hoping everyone's all right with that piece. Come up with your sigma means add. This is the starting input. This is the ending input. And this is the algebraic expression for the inputs to go in to get the outputs. And then you just add them together. Okay. So example 4, everybody. Let's see if we can knock out 3 sigmas here. So these are just 3 sums back to back. And let's see what we can do with this. So first and foremost, let's go ahead and get letter A. What I would do is write a big sigma. Now it should be noted, there are a variety of inputs to start with. for our purposes here, I would say start at 1. Start with the first input being 1. If something comes up and you want to start, you can start at 0. You might want to start at 2. Or theoretically, you can start at anything. That would change the expression probably a little bit there. But I would encourage you probably to start at 1. It's probably the most common. So I guess the way to do this is just start with that piece and then think about inputs and outputs. What I would do is start just focusing on the first 5 here. These are your inputs. Okay, and what do I do to those inputs to get the outputs? It looks like I don't do anything. So in terms of going from input to output, the input is the output, and our inputs are going to be represented as k. That's all. Instead of n, it's k. Because the nth term is really what goes up here. The ending term goes up there. And so I'm hoping everyone agrees if the inputs are the outputs, then the input that produced this 30 right here, of course, is 30. And so that's it. And based on what we did on example 3, does this right here look like we're going to do 1 plus 2 plus 3 plus 4, etc., all the way to 30? Yeah, it should. Good. You could see, obviously, expanded. Look how much more compact that is. And they mean the identical thing. Okay, very good. Let's see what we can do on the next one. So I just get a sigma ready. I start with the first term. I just think of the input as 1. And so I'm going to just kind of do this. 1, 2, 3, 4, etc., there. And now I have to figure out a little rule for us to go to from inputs to outputs. 1 to 5, 2 to 7, 3 to 9. So again, some of the same type of rules, so to speak, some of the same ideas that we've been going over now for a day and a half. So let's see what's going on with this particular pattern of numbers. It looks like I'm adding 2 each time. Repeated addition, of course, is multiplication. So repeatedly adding 2 means I'm probably going to get a 2k in there. Again, if my variable is k, let's do 2k. And here's, I guess, where we want to just be a little careful. So 2 times 1 is 2, get me to 5. 2 times 2 is 4, get me to 7. 2 times 3 is 6, get me to 9. So I'm seeing this as a 2k plus 3. Okay. Now the only dilemma here is I don't know what this piece is. I don't know which input produced the 21. But I can at least say, all right, well, that 21 was done by using some input, some value of k. And I hope you see here, if you go ahead and subtract 3 and divide by 2, it looks like we get a 9 right there. So that, I believe, is our 9th term, just the way I wrote it. And as I mentioned, theoretically, you can start at a different number and end at a different number and have a different expression and have it mean all the same thing. This, I think, as I said, is probably the most common version. So it looks like from the first term to the 9th term, and that's the algebraic representation of these values right up here. Wonderful. Okay, let's see if we can do one more. I'm going to start it out. I'm going to do a k equals 1 down there. And let's just see what's going on. Inputs to outputs, everybody. Let's get some good practice on that. Oops, sorry about that. This is the 3rd term. It's just getting ahead of myself there. So first term, 2nd term, 3rd term, 4th term, 5th, 6th, 7th, 8th, 9th. Looks like that will be the 10th term there. There's no ... so we know it's the 10th term. So that's nice. And let's see, it looks like to get the next term in each, I'd be multiplying by 2. So I have a feeling this is going to be a power, base 2. And let's see, though, this is 2 squared, not 2 to the 1st. This is 2 to the 3rd, not 2 to the 2nd. So in this case, it looks like I'm going to have to tweak each of my inputs first, then that'll produce the output. Because 3 plus 1 is 4, now 2 to the 4th will give me this. 4 plus 1 is 5, now 2 to the 5th will give me this. So I see this, and again, if you have an alternative way to do this, that's perfectly fine. There is definitely more than one answer. But just starting at 1, that's probably how we would have to do it. Maybe you should have started at 2 and gone to 11. 2 to 11, and it just would have been 2 to the k. So again, it's kind of fascinating. You can represent this a variety of ways. Okay, so please get used to that sigma notation there. Sigma means sum, and as you can see, it's a beautiful, compact way to pull that off. Hey everyone, thanks for listening to the lesson, of course. Let me know if I need to elaborate on anything as you looking and taking notes and doing the independent work.